Why do we exist? Life on Earth seems almost accidental. Our solar system is just a grain of sand in the entire galaxy, and our galaxy is just a speck of dust in the entire universe. As humans, we tend to feel pretty special. But are we really that rare? Some scientists say no. They argue that the conditions necessary for life are so finely tuned in our universe that we can't be anything but an anomaly. Either that or there are many universes out there with the same conditions, meaning we're actually quite common. If this is true, then maybe the question isn't why does the universe allow life? Maybe it should be, why do we exist? To answer this question, we need to take a journey through multiverses, wormholes, and parallel universes. So buckle up, because today we're going to find out if our universe proves that other universes exist. Part 1. The fine-tuning problem. Physics has revealed several coincidences that allow life to exist. First, consider the delicate balance of the hydrogen and helium binding energies. Stars produce elements heavier than helium in their cores. But for this process to occur, the energy generated inside the star must be at least 10 times higher than the energy required to bind those nuclei together. Otherwise, the end product would fly apart before any substantial amount could be produced. Turns out the hydrogen and helium binding energies are almost perfectly balanced, which allows for the creation of heavier elements and the eventual formation of Earth and everything else. Then there's the unique resonance in carbon-12. In the realm of nuclear physics, carbon atoms come in various forms known as isotopes. These isotopes differ in their neutron-to-proton ratio, leading to variations in atomic mass. Carbon-14, for example, has 6 protons and 8 neutrons, while carbon-13 has 6 protons and 7 neutrons. Among them, carbon-12 stands out with 6 protons and 6 neutrons. Its significance lies in the way its atomic nucleus interacts with electrons. Specifically, the balance of forces within carbon-12 creates a stable structure that strongly attracts electrons. This property is crucial for the chemistry of life. Carbon's ability to form 4 bonds allows it to create the complex chains and rings that are the building blocks of organic molecules. If carbon's binding energy were even slightly different, these stable bonds wouldn't form, and life as we know it couldn't exist. Next, consider the Higgs boson. In particle physics, the Higgs boson is associated with a field called the Higgs field. All other particles are thought to interact with this field, and these interactions give rise to the masses of those particles. The interesting thing about the Higgs boson is that its mass is surprisingly light compared to the so-called Planck scale. The Planck scale is a fundamental unit of mass in physics that represents the smallest possible measurable quantity. If the Higgs boson had a mass close to the Planck scale, gravity would be much stronger. And finally, there's the cosmological constant. The cosmological constant, represented by the Greek letter lambda, is a force that counteracts gravity and drives the expansion of the universe. It's often referred to as dark energy since it's a mysterious force we can see directly, but we infer its presence from its effects on the behavior of the universe. In Einstein's original equations for general relativity, the cosmological constant was a mere mathematical artifact, playing no physical role. However, in the mid-20th century, observations revealed that the universe was expanding, prompting Einstein to introduce the cosmological constant as a fudge factor to match his equations with what was being observed. Today we call this force dark energy, but here's the problem. The vacuum energy predicted by quantum physics should be 120 orders of magnitude larger than what we observe. That's the worst prediction in the history of science. Why is the number so small, yet not zero? Part 2. Weinberg's bold idea. In 1987, Nobel Prize-winning physicist Steven Weinberg made a radical proposal. He suggested that maybe we shouldn't be surprised by the value of the cosmological constant. Maybe it was never meant to be explained by a single elegant equation. Instead, perhaps our universe is just one of countless universes, each with different physical constants. Most would be sterile, lifeless, chaotic, or collapsing in an instant. But in a tiny fraction of universes, conditions would be just right for stars, galaxies, and eventually, observers like us. Now you might be thinking, wait a minute. Isn't this just a cop-out? Isn't this just saying that our universe is special because it happens to be the one where we live? Well, yes, that's exactly what he was saying. This reasoning is called the anthropic principle. It's not a new idea. Philosophers have been discussing it for centuries, but Weinberg put it on a pedestal in physics. In his 1987 paper, he used this reasoning to explain the small value of the cosmological constant. His argument goes like this: since the strength of gravity depends on the cosmological constant, a large value would make gravity too strong, preventing galaxies from forming. Therefore, any universes with a high dark energy value would be uninhabitable. Only in universes with low dark energy like ours could galaxies and life evolve. In essence, we find ourselves in a universe suitable for life simply because life is required for us to be here to observe it. Sounds circular, right? Well, that's one of the main reasons why anthropic reasoning is controversial. Weinberg didn't stop there. He also calculated the maximum size of dark energy that would still allow galaxies to form. Shockingly, his prediction came close to the actual value discovered a decade later. Could this be the first indirect evidence of a multiverse? How can that be? Let's go back to the beginning of the video. We talked about several coincidences that allow life to exist. Each on its own would be easily explained away. There are billions of star systems out there, so it's bound to happen sometimes. But together, they paint a remarkable picture. And here's the thing: physicists don't like coincidences, especially not coincidences that allow life to exist. For them, each coincidence needs an explanation. So what are the chances of getting this many coincidences in one place? You might say it's impossible, but it turns out it's actually possible if there are infinite coincidences. In other words, if there are other universes, some of them are bound to have conditions that are ripe for life. So is the multiverse real? Well, here's the problem. With coincidences, you can always invoke the anthropic principle. So you can't use them to prove the multiverse. And unfortunately, we're in the same situation with Weinberg's work. His calculation of the cosmological constant was based on the anthropic principle. So we can't use his result to prove the multiverse either. Limits and possibilities. But not everyone agrees. Many scientists dislike anthropic reasoning. It feels like giving up, replacing explanation with coincidence. They would prefer a deeper, testable theory that forces the cosmological constant to its tiny value. Still, the fact remains, Weinberg made his estimate before dark energy was even discovered, and he was close. That's hard to ignore. So what does this mean? If the multiverse exists, then our universe is just one bubble in an infinite cosmic sea. There could be regions of space-time with entirely different laws of physics. Some universes might be short-lived flashes of chaos. Others might give rise to unimaginable forms of life. The multiverse is not just science fiction. It's a scientific idea born from the mathematics of cosmology and quantum theory. One such idea is the eternal inflation model, which suggests that new universes or bubble universes are constantly being created. Another example is string theory, which posits the existence of multiple dimensions. Some scientists believe that these dimensions contain other universes. And what about wormholes? Wormholes are hypothetical tunnels that connect two different points in space-time. Some scientists speculate that wormholes could lead to other universes. But remember, we can't directly observe these things. By definition, they lie beyond our cosmic horizon. But indirect clues like fine-tuning, like Weinberg's calculation, might point us toward the truth. The discovery of dark energy itself was once unthinkable. Who knows what future experiments will reveal? Will we one day detect subtle imprints of other universes in the cosmic microwave background? Or will new physics explain the cosmological constant without the need for a multiverse? Conclusion. The multiverse remains one of the most daring and controversial ideas in modern science. It challenges our sense of uniqueness, our idea of one cosmos, one creation. Carl Sagan once said, "The universe is not required to be in perfect harmony with human ambition." Perhaps he was right. Maybe our universe is just one note in a far greater cosmic symphony. When we ponder the existence of the multiverse, we're essentially asking, are we alone? Not just in the grand scheme of the universe, but in the grand scheme of everything. The quest to understand our place in the cosmos is deeply ingrained in our nature. It's what drives us to explore, to innovate, and to seek answers among the stars. The idea that we might be part of a grander, more complex reality is both thrilling and humbling. Whether or not the multiverse exists, the journey to explore this question pushes the boundaries of human knowledge. It compels us to confront the deepest mysteries of existence and to refine our understanding of the universe and our place within it. As we continue to probe the depths of space and time, who knows what wonders and discoveries await us? Perhaps one day we'll uncover definitive proof of other universes, other versions of ourselves, or perhaps we'll find that our existence is truly unique. The thrill of discovery, however it unfolds, belongs to all of humanity. So keep looking up, keep asking questions, and who knows, you might just be part of the next great leap in our understanding of the universe. Thank you for joining us on Cosmic Reflections. Don't forget to like, share, and subscribe for more journeys into the mysteries of science, space, and existence. And let us know in the comments, do you believe in the multiverse, or do you think our universe is truly unique?